All right. Hello, everyone. I'm happy to introduce you to Delaney Dunne. Delaney did her undergrad at McGill University, where she worked with galaxy formation and evolution. Then she went to Caltech for her grad school. She's been working on line intensity mapping and specifically on COMAP, which is one of the leading experiments on line intensity mapping. And it's also exciting to say that now she's been going to a new position at McGill as a postdoctoral fellow. What's the name of your fellowship? TSI? Yeah. Fellowship. And she'll be starting next fall. And I'm happy to see what she's going to show us today about COMAP and line intensity mapping.
Perfect. All right. Am I mic'd right now? I can't tell. Beautiful. Okay. Thanks, everyone, for being here. Yeah, my name's Delaney. I'm in my final year at Caltech, and I have done most of my PhD working with this line intensity mapping experiment, COMAP. So that's what I'm going to talk to you about today. I'm going to start just by introducing the concept of line intensity mapping as a whole, because it's still kind of a niche field. A lot of the time, people don't even know what we're talking about when we say that. I'll describe the COMAP experiment, talk about sort of the mainstream COMAP science, which is the autocorrelation power spectrum, and then get into what I've been doing specifically within COMAP, which is combining the COMAP line intensity mapping data with other surveys of galaxies and doing sort of summary statistics that way. And then finally, I will do a little preview of our upcoming experiment, COMAP-wide. Okay, line intensity mapping. So in order to kind of introduce what this is, we need to start with the why. So the motivation behind this technique is sort of the large-scale evolution of the universe, which we kind of understand, right? Like I can put up a diagram of how the universe evolves from the Big Bang to today and feel that it's reasonably accurate. Like the broad strokes of this we have down. But there's lots of details that are still kind of yet to be figured out. And I'm going to focus in on two epochs of the universe's evolution. The first one is here, between kind of around redshift 2. So this plot I'm showing here is the star formation rate density of the universe is on the y-axis as a function of time. And this is plotted with various optical and IR surveys. And you can see there's a really obvious peak right around redshift 2. This is pretty well established. The star formation in the universe peaks around this redshift. We call it cosmic noon, or the peak of cosmic star formation. But the why behind that is not super well known. So in order for star formation to peak, there needs probably to be some amassing of the fuel for that star formation in galaxies leading up to that. And that's actually much harder to do a sort of concrete census of over the full universe. Because you need to tally up all of the fuel in galaxies over all galaxies over a wide enough region of the sky that you believe that you're doing an accurate census. And so that is kind of an open question, is why this is happening. The other period in the universe's history where line intensity mapping really comes in is the Epoch of Reionization. So this is the process by which the neutral hydrogen that the universe was mostly made up of was ionized by the first galaxies, the first stars, kind of the first sources of ionizing radiation. And there are many open questions about this. Like even the exact period at which it starts and ends is not super well nailed down. But then also what kinds of galaxies are driving this ionization process? Is it the really big, rare, bright ones or the more common, fainter ones? How much ionizing radiation is being produced? How much is escaping galaxies? All of that is sort of not super well constrained. And again, we've got a theme here where we need to tally up what's going on over the entire galaxy population down to the very faintest objects. And so traditionally in kind of cosmology, galaxy formation, when you have a problem like this, you do a galaxy survey. So you point your telescope at the sky, you start seeing point sources typically. Hopefully you have a spectrograph so you can get redshifts as well. And you just start tallying where these objects are in 3D space and some of their properties like their luminosity, star formation rate, that sort of thing. The issue with that is completeness. So I'm showing a toy model here. This is for the CO luminosity function at redshift 3. And so this simulation here in this toy model is all of the galaxies that you would have access to with 100 hours of observations on the VLA. And that is, a lot of time on a huge community instrument. Like, good luck even getting that. But the issue is you're only seeing sort of 2/3 of the luminosity function. And we believe the faint galaxies are much more numerous. The actual universe might look something more like this. And so this is just because there's a certain limit below which your traditional galaxy survey can't see a galaxy. And if it can't see it, it can't add it to the catalog. It doesn't know it's there. So, this is a problem. The solution we're proposing with line intensity mapping is instead of treating galaxies like point sources distributed in 3D space, you intentionally blur out the resolution of your telescope and instead sort of treat them as a 3D fluctuation field. Like the CMB, but in 3 dimensions, or that sort of thing. And so these are point sources that we've intentionally confused, essentially. And so in a given resolution element in this 3D fluctuation map, you have all of the luminosity from all of the galaxies in your population contributing to that total luminosity. So you lose the information about the individual galaxies, but you gain this sort of robustness against completeness issues, where you gain an understanding of the entire population. You're seeing all of the light. And how you deal with losing information about the individual galaxies is you do summary statistics. So I'm showing here the autocorrelation power spectrum. That's sort of the canonical one, but there's lots of other fun games you can play to sort of extrapolate out information about the entire galaxy population from this fluctuation map. So that's line intensity mapping kind of in theory. In practice, this is a pretty new emerging field. This is kind of the landscape of experiments using this technique as of 2022. And the few things I want to point out are we're targeting many different spectral lines. So there's optical lines, like oxygen lines, Lyman alpha, H alpha. And then there's a huge field of C2 and CO kind of millimeter, submillimeter, and then into the centimeter wavelengths lines, and then covering a broad range of redshifts as well. And in this plot, again, as of 2022, the solid lines are experiments that are actively running, and then the dashed ones are funded and will be running, most of them in the next few years. Okay. Do we have any questions about that before I keep moving? Beautiful. Okay. So the experiment that I work with that's using this line intensity mapping technique is called COMAP. This stands for the CO Mapping Array Project. And so it is a project to map carbon monoxide, CO, through a big swath of the universe. This is our collaboration. We're pretty small for an experiment of this size. Our PI is at Caltech, my advisor Kieran Cleary, and then a lot of the instrumentation is also at Caltech. Our sort of lower level data analysis happens in Oslo under Hans Christian Eriksen, and then we have kind of theorists and other instrumentalists scattered all over the place on top of that. Okay, so CO is what we're specifically going after, carbon monoxide, and there's kind of galaxy formation reasons for that. So CO is a tracer of the dense molecular hydrogen in a galaxy. And that dense molecular hydrogen is the gas that is fueling star formation. It's kind of about to form stars. And so there's a known very tight correlation between the CO luminosity of a galaxy and its star formation rate. But also, a lot of feedback processes in galaxies act on the molecular gas by heating it up or disrupting it physically, that sort of thing. And so galaxy-wise, it's a really interesting tracer. And then finally, galaxies are complicated. There's lots of different gas happening, lots of different spectral lines being emitted. And so thinking of LIM as like a broader field, CO works nicely in complement with the other tracers that are going on. The other key thing is COMAP is specifically targeting this CO molecular gas around redshift 3. And so if we go back to this plot here, where I have star formation rate of the universe as a function of time, this purple shaded region is where we're looking. So we are looking at sort of the fuel that makes new stars as it's building up towards this peak in star formation is the idea. We're taking a big census of what's going on, what's fueling this peak. In practice, this means we're targeting CO 1 to 0 specifically, the first row vibrational transition of CO, around 30 gigahertz Ka band. So we're in here frequency-wise. And there's a little bit of CO2 to 1 interloping in our frequency band, but that's kind of our main contaminant. We have an R of about 1,000 spectrometer that we're using, and that's actually binned to science resolution. We have access to R of like 10,000 if we want it. And the full frequency range is 26 to 34 gigahertz. So this is what the instrument looks like. It is at the Owens Valley Radio Observatory in California. It is a dish that used to belong to the Karma array that we've taken and repurposed, so it's 10.4 meters. And kind of the main guts of it are this 19-feed focal plane array. So essentially what this is each of these feeds has a totally independent receiver chain, mostly independent, but essentially it's taking an independent measurement of the sky. So it's a total power instrument. You just get like the power in your beam in the region of sky you're looking at, and as you scan over the sky, you're taking 19 independent measurements of that at any given time. You improve your sensitivity a lot. These are our fields. There's 3 of them, totaling about 12 square degrees, or 60 million cubic megaparsecs at redshift 3. They were chosen to be like far away from galactic and other sort of continuum foregrounds, and also to overlap with this other survey, HETDEX, that I'll talk a lot more about later. And we are, at this point, quite sensitive. So our best voxels, best 3D pixels at this point are around 25 microkelvin. Because of our scanning strategy, there's sort of a huge inhomogeneous noise response across the fields. But the best voxels are 25 microkelvin. And here's the timeline. So we started observing in 2019. Anytime I show you COMAP data today, it's going to be from the first 2 seasons combined. So our first season 1, our first 13 months, that was kind of a commissioning run. We learned a lot about our scan strategy, that sort of thing during that time. And then season 2, after that, we took that information and were able to like improve our overall sensitivity by like a factor of 3. So yeah, season 1 plus 2 are what I will be presenting to you today, but we are still observing. Season 3 is ongoing, and we have recently been funded for a new instrument that we're calling COMAP Wide. It's kind of a near duplicate of the Pathfinder instrument. I'll talk about it at the end of the talk. Okay, and I'm just going to flash this up in case people are interested. So we are also performing a galactic plane survey, mostly looking for radio recombination lines when we're not looking at our cosmological fields. I am not an expert in this, but if you have questions, ask, and I will try my best. Okay, any questions about COMAP? Yeah.
As someone who does not really do any radio stuff, what's the cause of the correlations with the offsets that are like on the diagonal slope?
Here?
Yeah, on the bottom.
That's just scan strategy.
Okay.
Yeah, so it's a line scan that's being performed, and lots of like continuum total power imaging strategy is getting rid of those stripes, but some still remain. Sweet. Okay, so I will then talk about the power spectra, which is sort of the main science result that COMAP's been producing. So in order to get into that, I'm going to just like very briefly touch on how our data reduction actually works. So sort of alluded to it a few times, but the telescope is scanning over the sky. And so that means that the like raw data stream is just power as a function of time, which you know where your telescope is pointing at any given moment. That becomes power as a function of position. So that's called time-ordered data, or TOD. And so the first steps in our data reduction pipeline are just to clean that up to get that like decent. So there's a couple of filters that are happening here. There is just an initial low-pass filter that we do. There is a filter that moves with the azimuth and elevation of the telescope. that gets rid of some atmosphere. There's a 1/f filter, this poly filter, and then just like a final PCA subtraction in the time-ordered data step. So all of that happens to get it looking from this like horrible sine wave mess to something more like this. And then from that clean time-ordered data level, we use a very simple noise-weighted binned map maker to make maps from the data. So these are what the COMAP maps look like as of season 2. We are currently pretty much entirely white noise dominated, which means there is no obvious signal in our maps, which is a bad thing, but that also means there's no obvious systematic errors in our maps, which is a very good thing. So we're kind of, as I'll show, we're getting down towards the sensitivity where we expect a signal. So the fact that we are still pretty much free of systematics is a really good thing. So we end up with these maps. They are mostly white noise. Some analyses get performed directly on the maps. But for the power spectra, how the obtaining the actual power spectra work is an internal cross-correlation process. So each of those feeds that are doing an independent measurement of the sky, we make maps out of them individually, and then we cross-correlate the maps from the different feeds. And that way, systematics that are unique to one feed that might be like residual in those maps fall out. And this helps a lot with the noise behavior of the power spectra. Okay, so here is the power spectrum plot. I'm aware this is a lot to look at, so I'm going to kind of break it down slowly. So on the x-axis here, we have spatial scale. We actually have inverse spatial scale. That's what K is. So we have big scales over here, small scales over here. And then the y-axis is the power. It's so how common are fluctuations in the overall CO density of the universe at that given spatial scale. And it's multiplied by K, multiplied by inverse spatial scale again, just to keep everything on the same axes. So like a flat power, one where there's like no preference for a given spatial scale, looks like a diagonal line on this plot. And then the lines that are on this plot, these are all models for the CO power spectrum at redshift 3. So the kind of first thing to pick up on is there's a huge difference between these different models. There's more than 2 orders of magnitude between them at most spatial scales. And that really truly is a reflection of the fact that we really don't know what the CO power spectrum looks like at these redshifts. We have like a couple of blind surveys with kind of 10 to 15 detections at these redshifts, and that's what all of the modeling is based off of. So these are mostly the bright end of the luminosity function. These models are basically entirely extrapolated towards the faint end, and that's what's causing most of the discrepancy here, is there's this huge uncertainty in like how many faint galaxies there are in the universe in CO at these redshifts. So in more detail, the models we break up into 2 components. So I'm even gonna, so the small scales are dominated by what's called shot noise. If you're a cosmologist, we would love to detect even that, so it's shot power to us. But this is sort of like stochastic individual galaxies popping in and out. And that would be a flat line, so it looks like a diagonal here. And so the pickup on this end for all of these models, that's the shot power component of the power spectrum. And then on the large scales, you're dominated by cosmological clustering. So this is the underlying matter power spectrum multiplied by this clustering amplitude, we call it, which is just the temperature, so the brightness of CO times the bias of the galaxy squared. So this is kind of cosmology. There is cosmological information in this side too, but if you're going after like the matter power spectrum, that sort of thing, it's this side of the plot that you want to look at. Okay, so those are the models. Yes?
Hi. I understand the vertical difference between the season 1 and season 2 of COMAP. I also noticed there's a scales difference between the 2 seasons. So your previous season had a higher scale, so why is the new one not going?
Yeah, give me 2 minutes and I'll get into that. But essentially we there was still some residual things happening in our largest K scales. There's very few modes there, so they're really susceptible to systematics, so we excised them from this analysis. Yeah, so yes, yeah, the other huge thing on this plot is the data. So there's a bunch of upper limits here. There's the brown ones up at the top. Those are indeed the first season of COMAP data, where we were kind of able to like tentatively rule out some of the bright models. There's also the blue points over here. These are from another CO experiment called COPS that mostly used community interferometers, like the SZA, ALMA, KARMA, those sort of instruments. And so they, because they were interferometers, were mostly sensitive to smaller scales. Those are the blue points. And then the white points are the COMAP Season 2 power spectrum constraint. So these are the tightest limits we have on the CO power spectrum at these redshifts. They're kind of touching they're not really touching, but they are starting to get close to the kind of family of models that we believe are reasonable, which is the ones that are kind of around 10 to the 3 over here. They are much lower than the COPS points in this representation, but they're actually not formally in tension with the COPS estimate for the shot power, which it kind of keeps going up that way. It's like there's a little bit of a discrepancy, but it's not a formal tension. And the final thing is we are spanning scales ranging from the shot power, but also we are getting a little bit into the matter power spectrum, the clustering power regime of the power spectrum. And hopefully, as we sort of analyze the data more in depth, we're able to recover some of those really low K bins that are missing from the season 2 analysis. Yeah.
Yes, I have a question. One of the white points is not an upper limit.
Yeah.
I noticed. Can you explain?
So that, what is happening there is there are 2 sigma upper limits. They're 95% upper limits. One of the bins that we had it was like at 2.3 sigma excess. And so just for like, fidelity and all that, it is plotted as a point because it is above a 2 sigma upper limit. But we did a bunch of like probability to exceed tests and stuff, and we don't believe it's like indicative of actual signal. Just like when you have this many K bins, there is a chance that one of them is going to be kind of 2.3 sigma above nothing at all. So yeah, that's why that's plotted like that. I think it's a similar story for the 2 COP spins that are plotted as detections as well. Yeah.
Hi. You mentioned this is at redshift 3, but has this been done at lower redshifts? So do we have a handle on what type of models to expect?
Not really.
So this is the only redshift regime this has ever been attempted?
Yeah, there's been like the sort of blind survey efforts are a little bit better at slightly lower redshift, but there's not been like a comprehensive power spectrum at any redshift.
Thanks.
Yeah. All right. Okay, any final questions on that? Beautiful, okay. So now we're gonna get into what I do within COMAP, which is taking the line intensity mapping fluctuation data from COMAP and combining it with external galaxy surveys. So these are both probing the same region of the sky. They're just different ways of measuring the large-scale structure. And so you have this kind of 3D fluctuation cube, and then you have also in the same region like individual points that correspond to galaxies in your galaxy survey. So you have two different sources of information. There are many ways in which you benefit from combining those 2 sources of information. The first one is just you have improved sensitivity. You're adding information. You're also much more robust against systematic errors. So those could be astrophysical systematics, like spectral line interlopers in your data. This could also be instrumental, standing waves, that sort of thing. So having an independent source of information means that likely any systematics are going to be unique to one survey or the other, and they'll fall out in the combination. And then finally, as I've been saying, galaxies are complicated, so studying them with multiple spectral line tracers at once is a good thing. You get information from that. Okay, there's tons of ways you can do this, and sort of more are being explored all the time. The canonical way is a cross-correlation, just the sort of two-survey analog of the auto power spectrum I was showing you earlier. There's also simpler strategies you can use, like stacking or co-addition. I'm going to be talking mostly about that. And there's kind of more out there strategies, like one-point statistics, this deconvolved distribution estimator, that sort of thing. So I'm going to talk about stacking and get into cross-correlation a little bit. Stacking is based on a couple of very simple assumptions. It's just based on the idea that the objects in your galaxy catalog are tracing the underlying large-scale structure somehow. And that means that regions of your line intensity map that contain an object in your galaxy catalog are probably going to be bright in your line intensity tracer, just because even if the object itself isn't bright, it's going to have neighbors that are bright. And we are looking at scales, like one of our pixels is 2 co-moving megaparsecs across. Like they're very big scales. There's many different galaxies getting involved here. So it is a little bit different from kind of traditional astronomical co-addition, which is done all the time. So all you do is you take the regions of your line intensity mapping data cube that surround one of the objects in your galaxy catalog. You cut them out of the map. You do this in 3 dimensions. I'm just showing 2 here for kind of ease of diagramming. And you just average them together. And so this way you are, in theory, maximizing your signal under the assumption that your galaxy catalog is tracing the large-scale structure. You're beating down your noise through averaging. And you end up with this sort of large 3-dimensional cubelet, we call it, that you can look at and see if you see any larger scale fluctuations. Or you can say, okay, I expect most of my signal to lie sort of within 1 or 2 beams of the center, or 1 or 2 frequency channels of the rest frequency I'm looking at. And then sum over that aperture and end up with a summary statistic that you can, like a single number you can compare. And that number is kind of weird. It is the average luminosity in your intensity mapping tracer of the region surrounding the objects in the galaxy catalog. So it is very biased compared to just like a straight up average. And you're also kind of imposing a spatial scale upon it with the size of your aperture. But it's like still interesting and you can get a lot of cool science out of this. So that's the idea behind the stack. I just said a ton of assumptions in order to introduce that idea. And then also, this is a weird statistic. We weren't like totally sure what we would be looking at once we actually performed it. So a big part of my PhD has been developing this simulation suite in order to test these assumptions, see what the output looks like. There were simulation suites existing. There are tons for like mocking a line intensity mapping data cube. What was missing was one that could simultaneously do a data cube and a galaxy catalog in a different line tracer. And so the sort of 2 things that it was really important that this picked up on were the sort of large-scale relationship between both the intensity mapping tracer and the galaxy catalog tracer and kind of the underlying large-scale structure. But then on the level of an individual galaxy, the interaction between the 2. So I'm going to show you stacks on quasars and on Lyman alpha emitters in a bit, and like especially Lyman alpha emitters. Galaxies that are bright in Lyman alpha are actually probably very dim in CO and vice versa. And so that interaction, how that affected the stack, it was really important that we recovered that. Okay, so this is what a highly futuristic stack will look like, we think, based on the simulation pipeline. I'm going to be showing plots like this a lot. So this is that 3-dimensional cubelet binned across the center frequency channels into a 2D image here, and then binned across the spatial aperture where I expect most of the signal to be into a spectrum here. And that's, again, just for representation on a flat slide. So this is what we think the stack will look like. The kind of key thing to pick up here is this is the size of the COMAP beam in the corner here. And there's actually signal extending beyond that. This is not a point source. And this was kind of very interesting to us and very peculiar to us. This is actually underlying large-scale structure that we're picking up on. So it really is the clustering of the galaxies around the objects in your galaxy catalog that's really causing most of this signal. And I'm going to sort of prove that to you in a couple of different ways. But just for context, this box that's up there, that's 0.25 co-moving megaparsecs, inverse co-moving megaparsecs, that corresponds to 25 co-moving megaparsecs at these redshifts on a side length. So this is, multiple galaxy clusters combined together. It is very big. Okay, so almost all of this signal, why it's so extended, why it looks like clustering, does not come from the object that's actually in the galaxy catalog. It's not a straightforward coaddition on those objects. It's very much dominated by the other objects, like the other galaxies surrounding that galaxy. So this plot is one way of showing that. The purple line, that's just the spectrum of the stacked cubelet. That's sort of similar to what I was showing before, but with no noise in it. This orange spectrum here is the spectrum of the object that's actually in my galaxy catalog. So the signal is pretty much entirely dominated by other galaxies in the stack, and that has lots of implications. Here's one other way of showing that. So again, this is the 2D spatial image here. And this plot is a histogram of the number of other galaxies that are in each 2D pixel in this image. And you can see the center one has 20 galaxies total in it. And there's sort of no less than 8 all the way through the aperture. So yeah.
I think you said it, but can you go back? What's your input catalog? Is it stellar mass selected or Lyman alpha flux?
So this one here, the simulations I'm showing are Lyman alpha selected. So there's a prescription for...
Star formation rate.
Yeah, essentially, yeah.
Yeah, okay.
Yeah. But you get a similar thing when you're looking at like a quasar selected one. It's actually much more intense when you do that. Yeah.
When you stack, it's not only on the equivalent of the instrumental beam you have.
Yeah, so the aperture that I end up summing over is sort of set by looking at the simulations. And I picked one that maximizes the signal to noise in these simulations, which is, it's larger than the instrumental beam. This one here is 7 by 7 I'm showing. I actually ended up with 5 by 5 voxels, which is it's like 2.5 times the size of the beam. And you could go larger. You're summing in more noise as you go larger.
Right.
The signal keeps falling off. It definitely doesn't plateau there.
Okay.
Yeah. Alright. So yeah, in this aperture, this is a Lyman alpha representation. There's around 217 neighbors on average. For quasars, there's more like 260, and they tend to be higher mass on average. So this really is a clustering signal that I'm going to be showing you for the rest of the talk, which is great for line intensity mapping. Like, that's what we're going after. But it does mean that like you can't straightforwardly say, okay, we're looking at the signal from the galaxies in the catalog. Yeah.
Is it like 2 halo term or 1 halo term when you speak clustering at these scales? Does it make sense?
2, I believe, yeah.
Okay.
Yeah. Okay. And so there are implications of this in terms of like designing a line intensity mapping stack experiment. The first one is you want a galaxy catalog that is as biased as possible, because it is the clustering around the objects in your catalog that are driving your signal. If you have more objects and they are brighter, then you get it's like almost a factor of 3 increase. These are different simulation realizations, but they all have constant noise. So like a scale factor here is a scale factor in luminosity. And yeah, that's just because you have more halos surrounding your center object, and they are bigger overall and tend to be brighter overall. And the other implication of this is that the actual like galaxy level interaction between your 2 tracers doesn't matter that much. So it matters a little bit more for like a really biased object, like a quasar-like survey, That's the bright violins on this plot. But still, it's like kind of less than 3 sigma difference. I guess I should explain this plot. This row here is the correlation in the scatter between the 2 tracers. So if rho is 1, that means that a really bright object in the line intensity mapping tracer, in CO in this case, would also be like the brightest object in the distribution for the galaxy tracer. Rho is -1 is the opposite. One galaxy tracer that's really bright is going to be dim in CO. And because the actual like CO luminosity of the objects selected in your galaxy catalog don't matter that much, the correlation between the 2 also doesn't matter that much. There's pretty little dependence on this, especially for like a Lyman alpha-like survey, which is the default that's plotted here. You can see almost no variation across this plot because you're really just using those objects as tracers of the underlying large-scale structure. Yeah.
And remind me what simulation you're using and what the prescription was for how you assign CO to.
Yeah, so this is, it's my simulation suite, which is based on Lim Lam Mocker, so Dongwoo and Patrick's simulation suite. So those start with a peak patch dark matter catalog, and then it's CO luminosity as a function of halo mass is how CO is painted on. So that can go through IR luminosity or star formation rate. Here it's going through IR luminosity. So it's like you start with a dark matter mass, you say, okay, an object of this mass is probably going to have this IR luminosity, and then you do a conversion between IR luminosity and CO to get the CO luminosity. Okay. For the galaxy catalog, it's just abundance matching to luminosity functions. I think, yeah, okay. That's the last theory slide, so any other questions on that?
How was their simulation benchmarked? Like, what data were they using?
So the CO model is compared to, it's like a huge amalgamation of COPS and then aspects fibs, and then the CO results are all folded into that. It's the like COMAP fiducial model.
Yeah, okay.
Yeah. All right. So now I'm going to show you some actual data. So the kind of first analysis, and the one that I recently published in this theme, is a stack on quasars from EBOS and from DESI. I kind of combined the 2 catalogs. Between the 2 of them, there are 230 quasars across the 3 CO map fields. And when you do that whole stacking process on this catalog of quasars, you get something that looks like this. So this is not a detection, unless someone sees like a miraculous fluctuation in there, but we don't believe it is one. The thing is, this is actually a very sensitive non-detection, to the point where this is where the fiducial model for the stack signal should be. So we are reaching the point where like we probably should be seeing something if the fiducial model is correct. So this is even after like a ton of different factors that could be like experimental or astrophysical that might otherwise be attenuating the modeled signal in the actual observations. So things that are in here are the CO map, like on top of the like galaxy tracer dependence at the per galaxy level and the like overall distribution of the 2 tracers. On top of all that modeling stuff, there's the CO map transfer function. There is sample variance in the models. There is velocity attenuation. So quasars have like known large in or outflows that can really offset their optical lines from the CO. That's accounted for. That attenuates the signal a little bit. There's a known pointing uncertainty in CO map that also attenuates the signal a little bit. We have, as I mentioned at the very beginning, there's some CO 2-to-1 line interlopers that are falling into our frequency range. That doesn't attenuate the signal, but it does increase the uncertainty. That's accounted for. So after going through all that, for a variety of different CO and quasar models, the brightest models are being excluded at kind of 3 to 4 sigma. So very tentative. I'm not going to like hang my hat on an exclusion of that level, but we are sort of definitely starting to touch that model space in a very concrete way. yeah, so this COMAP fiducial model is the one I've kind of been talking about and what I've been showing in all of the plots. And so for one quasar model, that's above 3 sigma. For the other one, it's not. And then there's kind of the rest are various. But we're starting to touch the brightest models for sure with the stack. The huge caveat to this is not a straightforward constraint on the CO models alone. So all of the stuff I've been talking about with the dependence on like the quasar positions, the clustering around the quasar positions, the environment around quasars, all of that is also going into these numbers, and it's completely degenerate because it's just a single value. And so I cannot sit here also and say like we are ruling out the fiducial model at like greater than 3 sigma for one quasar model because there's this additional dependence on the environment surrounding quasars. So there's sort of other astrophysical explanations you could also imagine for this that aren't accounted for in the simulations. So things like, at low redshifts, dense environments are known to quench star formation. This hasn't necessarily been observed at redshift 3, but if it was in there, that could also be causing a result like this. Or like, quasars can have jets. Those cause feedback in the areas around them. Those jets can be large. That could also be causing a result like this. So things like this have definitely not been ruled out and are totally degenerate with the CO model just being too bright. So that's also stuff that we need to think about. So the way that we break that degeneracy, there's sort of two things we're looking into. The first one is just stacks on different catalogs of galaxies with different biases, different environmental dependencies, that sort of thing. And then the second one is going to a full cross correlation and getting access to other spatial scales where you suddenly just don't have one number. So next step for me, what I am working very hard on right now is assembling a catalog of Lyman alpha emitting galaxies from HETDEX, which is the Hobby Eberly Telescope Dark Energy Experiment. It's a large blind LAE survey intended for measuring dark energy quantities that our fields overlapped with. It was we designed our fields to be cross-correlation partners with HETDEX. So this is great. It is a very different galaxy tracer for sure. LAEs are biased very differently from quasars and tend to be in different areas of the sky. So that attenuates the signal, but we also have many more LAEs in our fields. And those factors actually almost entirely balance out. This is super preliminary, but we're seeing kind of a similar level of very tentative model exclusion in the LAE stack as well. And then the other thing you can do is you can cross-correlate. So this is kind of the ultimate goal, because with stacking, you do just have that one number. It's one spatial scale that you're sensitive to. You're summing over everything else. Cross-correlation, you have access to other spatial scales. This is just a forecast CO cross LAE cross-correlation. Why I have not done that yet is because the HETDEX footprint on the sky has a ton of structure in it. And so stacking is not sensitive to that. The cross-correlation is. And so there's lots of disentangling that's going to need to happen there, which is why stacking is super nice. It's like a really preliminary measurement of this sort of thing to look at. Yeah?
Is that your window function, or like the gaps? Did HETDEX not observe that? Or?
Yeah, so HETDEX, it's a fiber-fed IFU. So it's like this hexagonal shape that goes on the sky. It's made of smaller squares within the hexagon, and then they do 3 fiber dithers within each hexagon. So there's 3 levels of spatial structure in the window function. And then on top of that, the COMAP footprint is also not super homogeneous at all. And so, yeah, there's structure there for sure. Okay. Yes.
What's that stripe on the bottom?
Oh, yeah. So this is, between halfway through season 2, we had to change our scanning strategy because we were burning through our gears too fast. Yes. So we slowed down the scanning speed, and that means that the footprint doesn't overlap perfectly between the parts of season 2. And that also means that we're spending more time on the edges of the map. And so that's what that weird stripe is. Okay, so in the final kind of like 5 minutes, I'm just going to flag post what we are doing next, which is trying to push COMAP and CO intensity mapping towards the Epoch of Reionization. So we're doing this through an experiment called COMAP wide, and what this is it's basically an exact duplicate of the existing Pathfinder experiment. So it is a 10.4 meter X-Karma dish at the Owens Valley. It is a 19 feet focal plane array. It's covering the same frequency range. But the thing is, as I've said a few times, in this frequency range, you have CO1 to 0 redshifted to around 30 gigahertz from around redshift 3. But then also CO2 to 1 from around redshift 7 is redshifted into the same frequency range. So for our redshift 3 science, this is an interloper. This is an astrophysical background that we need to deal with. But this is astrophysical signal also. And so if we're able to isolate the 2 to 1 emission, we can study the Epoch of Reionization directly. The CO1 to 0, we think, is about 3 times brighter than the 2 to 1, optimistically. And so you can't really, in this frequency range, do a straight autocorrelation and expect to get 2 to 1 out. And so what we've designed this experiment for is a cross correlation with 21 centimeter. And so we'll be working with LOFAR. We'll have a wider field at the north ecliptic pole. My slides here says 400 square degrees. That's actually a little bit out of date. It'll be somewhere between 20 and 40, we think. That's a little bit in flux depending on them. And that's for, the wider field is for mode matching. So the 21 centimeter experiments cover much larger fields, but they tend to have worse spatial resolution. Our spectral resolution actually matches pretty well with the LOFAR spectral resolution. And so if we cover the sort of small fields that we're using for redshift 3, there'll be only a few Fourier modes in the power spectrum that are in common between the 2 experiments. And you only get sensitivity in those areas. So duplicate, wider field, targeting CO2 to 1 around redshift 3. Or redshift 7, sorry. And this is going to be an interesting signal that's going to take a lot of disentangling because the 21 centimeter emission that LOFAR is targeting, this is coming from neutral hydrogen gas. And the Epoch of Reionization is the process of the galaxies in the universe ionizing that hydrogen gas. So the regions surrounding galaxies, which is where the CO is emitted, those will not have 21 centimeter signal immediately around that because it'll all be ionized hydrogen. And the 21 centimeter emission will be coming from the sort of regions that haven't yet been touched by an ionizing source. And so you get this interesting signal where on small scales, like within these ionizing bubbles surrounding the galaxies, you have an anti-correlation between the 21 centimeter emission and the CO emission. And then as you go to larger scales, they become correlated because they're both tracing the underlying large scale structure. So the dream is you get a power spectrum that spans all of those scales, and there will be a crossover point where you go from anti-correlation to correlation. And that size is the size of the ionizing bubbles during the Epoch of Reionization, which is super cool. That's something that people are absolutely searching very hard for. Ideally, you'd also get this as a function of redshift, so you can measure how that evolves, how the process of reionization happens. We don't believe we are going to get any of that with this first experiment. The signals are just too faint, but it is going to be sort of the first attempt to start measuring this kind of characteristic power spectrum signal. So this is a very early forecast for what the signal might look like. So it's the cross power spectrum at a given spatial scale, so fixed to 1K, K of 0.1, as a function of redshift. These are done by Patrick Bracey and Hannah Fronenberg at UChicago and SMU. And so the cross spectrum, that white triangle is kind of what we expect our upper limit to look like. Again, super preliminarily. So even in these forecasts, we're not going to see anything. But this will be, again, the first limit of its kind. And by making assumptions about the correlation between CO and 21 centimeter, which you can do using modeling. You can kind of back out a limit on both the 21 centimeter autocorrelation power spectrum and the CO auto power spectrum from your cross power spectrum. And so we'll be able to place limits on both of those as well. I think that's the last slide on that. So I'm just going to leave the summary up here. CO is an active line intensity COMAP is an active line intensity mapping experiment. We're looking for molecular gas just before star formation peaks in the universe. And we are doing that in a variety of ways, including lots of ways combining galaxy catalogs with the COMAP data. And we will hopefully have future stages of the experiment very soon. So thank you so much.
Can you say more about the tension on the power spectrum limits between COPS and COMAP? Like,
Yeah.
why does it not worry you?
So I can pull that back up. The shot power limit from COPS, it's based on combining all of their K-scales, which span actually further into the shot noise regime than is shown on this plot. And it's based on modeling. It is model dependent. And so by combining all of that and integrating it with a model, they were able to sort of say, okay, we think the overall shot power is this using like a Bayesian analysis. So it was like a constraint that they found, not just a limit. And we are, I think it's like 2 sigma in tension with it, so it's not just not a formal exclusion yet. We're just not sensitive enough to say anything concrete. Yeah.
When can we expect season 3 data, do you think?
Pardon?
When can we expect the season 3 results?
That's a really good question. So all of the low-level data analysis is being done by 2 grad students, now postdocs in Oslo. And they both graduated in the past 6 months, so they haven't had time to look at it at all. So hopefully within the next few months, we're gonna start an active campaign. We certainly have almost 2 years of data in the can. I think it's 16 months of good observations. And so the data's there, it's just a manpower limit right now. Yeah.
I have one question. What do you think are the biggest constraints for your analysis in terms of simulations? What do you wish you could see more accurate from simulations or better?
Yeah, I think so.
Sorry.
Yeah, the question was what's the biggest constraint from the simulation side for the analyses? What should I be simulating better? And the sort of overall galaxy halo connection in the simulations is super rudimentary. It's literally just the 2 prescriptions for assigning luminosities to dark matter halos, and then this correlated scatter between them. There's no dependence on environment. There's not really any redshift evolution, that sort of thing. And so, I think for a big clustering scale like this, it's a good first attempt. But when we're so affected by the astrophysics, and in particular, really selecting on regions that are very special astrophysically. I think we're also selecting on regions where the really straightforward one-to-one correlation falls apart. Yeah. And so I think that's why you can't really draw any straightforward CO conclusions from the simulations, is they're just not really reflecting those behaviors. Yeah.
And for the stacking, have you forecast what you could have with Euclid, for example?
Yeah, Euclid. So the north ecliptic pole that we're going to be looking at with COMAP wide is going to be amazing. There's another 40,000 HETEX objects there. That's where the Sphere-X deep field is. That's where Euclid is. Euclid deep field is. So there's plenty of other opportunities for cross-correlation targets there. Euclid is going to be a tricky one just because of spectroscopic resolution. So we deal extremely well with continuum foregrounds. They're basically not a problem for us at all, but that's because we destroy any signals that are correlated across frequency more than 1 gigahertz. And so that's a delta Z of 0.05, I think. And so that's the Euclid photometric redshifts are going to be worse than that. And so it's most of the signals from Euclid is going to be at scales that we are actively removing from our data. And so if we want to do a cross correlation there, we're going to have to think more carefully about how we're doing our data reduction. Yeah. But it would be really cool. Same with SphereX. SphereX is a little bit better, but it's still definitely a problem. There's sort of only a few modes that overlap.
All right, so let's thank Delaney again.